Dear friend, hereafter in few of the video lectures we are going to solve the numericals based on the fluid mechanics. The numericals I am going to take in these lectures are very easy, formula based. With these numericals again we will revise the formulae that we have learned in the previous video lectures. Uh, to solve the numericals, you need is the practice. Therefore, what I expect from students is that you go through these numericals and try it independently in your own in your own notebook. Now we will go one by one. Now here the first numerical is find the pressure 200 below the surface of ocean if the pressure on the free surface of a liquid is 1 atmosphere, density of water is 1060 kilogram per meter cube. The density of water, we used to take it as 1000 kilogram per meter cube in SI unit, and in CGS system it is 1 gram per centimeter cube, but it's a water in ocean which is supposed to be the hard. It used to have a salt in it, therefore the density is little bit more, therefore instead of 1000 it is given 1060 kilogram per meter cube. Dear friend, the things are very simple here. Let us consider it's ocean, that is liquid in ocean, and here we have to think of at a depth h from the surface which is equal to 200 meter. We have to determine what will be the pressure. Now pressure at this point is, let it is P. This pressure is nothing but the pressure on the surface, which is P0, that is atmospheric pressure, plus pressure due to the depth of the liquid column or the height of the liquid column from that point to the surface. When I say it's a height, it is from a point to the surface. When I say it is a depth, it is from the surface to the point. And the job is very simple. The total pressure at a depth is P, which is sum of atmospheric pressure plus the pressure due to the liquid column. Pressure due to liquid column is H into rho into G, where H is the depth of the liquid column from the surface, rho is the density of liquid, and G is the acceleration due to gravity, and P0 is the atmospheric pressure. One should remember that the atmospheric pressure, which can be measured with the help of barometer, it is height of mercury in the barometer H, density of mercury in the barometer D, and acceleration due to gravity. At normal atmospheric pressure, height of mercury in the barometer is 0.76 meter, that is 76 centimeter. The density of mercury is 13,600 into acceleration due to gravity 9.8 meter per second square. Therefore, hereafter you have to remember these figures and the product of this one, it is 1.013 into 10 to the power of 5 Newton per meter square, and this we call it the 1 atmosphere. 1 atmosphere is 1.013 into 10 to the power of 5 Newton per meter square. Now I have to find out the pressure at a depth H and pressure at a depth H. The total pressure is equal to, I should write this as atmospheric pressure, just what we have determined. It's 1.013 into 10 to the power of 5 plus the depth below the surface of ocean is 200 meter, therefore I should write it as 200. Then the density of a liquid, obviously liquid in the ocean is the ocean water, which has a density of 1060. As we know, acceleration due to gravity is 9.8. Therefore, I should write it as 1.013 into 10 to the power of 5 plus. What I should do here is that for the addition, again I need a 10 to the power 5 common. Therefore, I will take 3 from this one and 2 from this one, and it will be 2 into 1.060 into 9.8, and the total into 10 to the power of 5. Here 10 to the power of 5 is common, and here we will get it is 1.013 into the product I will get here 20.776, that is 20.776, and the common of these two is 10 to the power of 5, and the expected answer here I will get here is 21.789. 21.789 into 10 to the power of 5 Newton per meter square. Therefore, pressure at the depth is 21.789 into 10 to the power of 5 Newton per meter square. Only thing that you have to do is that take a product of this, and it should be equal to 20.776. You have to check that, and thereafter it's a simple algebraic sum of these two. Sorry, here I should write a algebraic sum of the two, and 10 to the power of 5 is common, and then you will get the expected answer. Now we will go for the next numerical. This problem is based on Pascal's law. What is the Pascal's law? In an incompressible liquid enclosed in a pipe or in a container, the pressure inside the liquid is equally distributed, undiminished. Therefore, pressure at every point of the liquid will be the same. This is the simple Pascal's law or the Pascal's principle. What the problem says here? Go to the stem of the problem and understand what is given to us and what is to be determined. For that, we will read the problem at first, line by line, and then we try to solve it. In a hydraulic lift, the input piston had a surface area of 30 centimeter square. Here input piston has an area of A1 which is given 30 centimeter square, and if you need it, you may convert it into SI system. Centimeter is the CGS unit of length, and meter is the SI unit of length, and 100 centimeter is equal to 1 meter. Therefore, 1 centimeter is equal to 10 to the power of minus 2 meter. As it is square, 10 to the power minus 2 square, it should be 10 to the power minus 4 meter square. If output piston has a surface area of 1500 centimeters square, therefore uh, the output piston we are taking on the other side has an area of 1500 centimeters square. As we have done previously, it should be 1500 into 10 to the power of minus 4 meters square. Now, what the force applied to the input piston? If a force of 25 Newton is applied to the input piston, therefore force on input piston is 25 Newton. Calculate the weight on the weight is nothing but a force. Therefore, we will calculate the force on the other. What it should be? F2. As I said, according to Pascal's law, whatever is the pressure applied at one point of incompressible liquid, it is equally undiminished distributed throughout the liquid. Therefore, pressure at all points will be the same. Therefore, pressure at the input side is F1 upon A1 and pressure on the output side is F2 upon A2, and hence you will get a F2 is equal to, I should write it as A2 divided by A1 into F1, and it comes out to be equal to F2 is equal to what A2 is here. A2 is 1500. It's 1500 divided by 30, 10 to the power 4 in the numerator and denominator get cancel, and it should be equal to multiplied by the input force, that is 25 Newton. It should be equal to this 0 get cancel, and it's 3 5s are 50 and one more 0 is that. Therefore, you will get 50 into 25, and it should be equal to 1250. The output force output weight will be 250, and it's a very simple thing that by applying a force of 25 Newton on one side, you are able to lift a force of 1250 Newton. It is almost 50 times more. This is the problem based on the Pascal's law. It's the application of simple Pascal's law. This problem is based on Stokes' law, and using the Stokes formula, we are able to get the answer of this problem. The problem is again very simple. You have to put the values and get the answer in the given formula. That is the only thing that you have to do. Calculate the viscous force acting on a raindrop of diameter 1 millimeter. Diameter of the raindrop is 1 millimeter, therefore its radius should be equal to half of the diameter. It should be 0.5 millimeter, and in CGS system it is 0.5 into 10 to the power of minus 3 meter. 1 millimeter is 10 to the power of minus 3 meter. This conversion you have to remember, it is needed there. Falling with uniform velocity. The velocity with which this raindrop falling is 2 meter per second. And one more thing that is given to us is the coefficient of viscosity of air is 1.8 into, power is remaining here 10 to the power of minus 5. I have to correct it as 10 to the power of minus 5. Newton second per meter square. I will correct here. It is into 10 to the power of minus 5. This much correction we will take here. What is the concept here? It's a raindrop. We know that it is almost spherical, little bulge at the lower level because of gravity, but almost you may treat it as a spherical drop, and when it falls through here, then the Air opposes its motion. The opposition by a force that is known as the viscous force or the viscous drag. And we know that according to Stokes, this viscous force is 6 pi eta r into V. Here F is equal to 6 into 3.14 into 1.8 into 10 to the power minus 5. The radius we have taken here as 0.5 into 10 to the power of minus 3 into 2. Actually 0.5 is what? 0.5 is nothing but 1 by 2. 1 by 2 into 2 or 0.5 into 2. It is 1. Therefore, immediately I will take this 0.5 into 2 as 1. What remains here is 6 into 3.14 into 1.8. 6 into 3.14 into 1.8 and 10 to the power minus 5, 10 to the power minus 3. It's 10 to the power of minus 8. There is addition of indices in multiplication. Therefore, minus 5, minus 3, minus 8. And this comes out to be by a simple multiplication. You will get an answer 33.93 into 10 to the power of minus 8 Newton. And divide it by 10 and multiply it by 10, you will get 3.393 into 10 to the power minus 7 Newton. Here is the problem which is based on the Newton's formula for viscosity, viscous force. What the problem is, a horizontal force of 1 Newton is required to move a metal plate of area 10 to the power minus 2 meters square with a velocity 2 into 10 to the power minus 2 meter per second. When it rests on a layer of oil 1.5 into 10 to the power minus 3 meter thick, find the coefficient of viscosity. This is the problem. Let us consider, for the sake of convenience, we will take this paper pad as a metal plate. Sorry, actually it's a paper pad, but we will take it as a metal plate. On this metal plate there is a drop of oil. Drop of oil is there, dropped on the oil. The drop of oil has a thickness of its a surface, and here is the drop of oil. The drop of oil will be like this one. It has a thickness of what this thickness is of 1.5 into 10 to the power of minus 3 meter. And on this oil drop, again we got another metal plate. This is another metal plate. It has to move on this one. It has to move with a velocity of 2 into 10 to the power of minus 2 meter per second. And this thickness is of 10 to the power of 5 into 10 to the power of 1.5 into 10 to the power of minus 3 meter. We have to find out the coefficient of viscosity. And one more thing that is given, this area of the plate. This plate has an area of 10 to the power minus 2 meters square. The job is again simple. What we will do here is we will substitute the values in the formula, and the formula will be like this one. The coefficient of viscosity, eta, is equal to it's a force per unit area per unit velocity gradient. The coefficient of viscosity is the viscous force per unit area per unit velocity gradient. Here the viscous force is of 1 Newton. It is equal to 1 Newton divided by, what is the area here? Area is 10 to the power of minus 2. Obviously it's a meter square. All the things given are here in SI system. Therefore there is no need of conversion here. The velocity is 2 into 10 to the power minus 2. Actually this term is velocity gradient. It is the rate at which the liquid flows with respect to the distance measured from the stationary lab. This is the stationary plate, and this is the distance. Therefore velocity is 2 into 10 to the power minus 2, and distance from stationary layer is 1.5 into 10 to the power minus 3. It's 1.5 into 10 to the power of minus 3. This denominator will go in the numerator, and what you will get here is 1.5 into 10 to the power of minus 3 divided by 2 into 10 to the power of minus 4. And at last what you will get here is 10 to the power minus 4. When it goes in the numerator, it will be 10 to the power of plus 4 minus 3 plus 1. It's 15 divided by 2. It should be equal to 7.5 Newton second per meter square. I hope you might have followed this one. It's again a simple formula. By substituting the values in the equation, you will get the required answer.